On this question, we want to evaluate the integral. We've got the integral of 1 over 5x plus 1 to the 6th power dx. So we're going to solve this with substitution. And usually with substitution, you want to let what is inside a parenthesis or in the bottom of a fraction or inside a radical, inside an exponent be what u is. So on this one, we can let u be equal to 5x plus 1. And I need to change, when I change the variable from x to u, I also need to change the dx to du. So I'm going to calculate the derivative of u with respect to x, and that's 5. So I'm going to solve for dx so that I can substitute in for that dx. And so I multiply both sides by dx and get du equals 5 dx, and divide both sides by 5. 5 dx equals du over 5. So now I'm going to substitute. And when I substitute, I have the integral of 1 over u to the 6th times du over 5. So I substituted in for 5x plus 1, and I substituted in for dx. And this gives me 1/5. So I factor out this 5 out of the integral. I'm going to use my properties of exponents to write this as u to the -6 du. And now I have it written in a form where I can apply the power rule for integrals. So I have 1/5 u to the -5th over -5. So that power rule for integrals is if you have the integral of x to a power dx, then you add 1 to that power and then divide by that power plus c. So that's what I've done. I've taken -6 and I've added 1 and divided by that value. So this is going to be, got to have that plus c, and if we simplify, this is -1/25 u to the -5th. And I need to bring back my original variable. I left off that plus c again. I need to bring back that original variable, so I'm going to use the substitution that I made before, and that's -1 over 25 times 5x plus 1 to the -5 plus c. And I can also use my properties of exponents again and make this -1 over 25 times 5x plus 1 to the 5th power plus c. So I want to try the same problem without substitution. Try to recognize the pattern without doing that u substitution. So when I take a look at this, what I'm noticing is that I've got this 5x plus 1 on the inside, and that's my inside function. And in order for me to proceed with the pattern of composition, so maybe I should write down the pattern I'm looking for before we start writing it there. So what I'm looking for is this pattern with the composition of two functions. So that composition is when you have f of x being an outside function and g of x being the inside function. And then we also need to have the derivative of the inside function. And if we have this pattern of the composition of two functions and the inside function's derivative being multiplied, then we can apply this antiderivative. It's a sort of the version of the chain rule for antiderivatives. And so what you do is you calculate the antiderivative on the outside function, leaving the inside function the same, and then having your plus c. So if we can recognize this pattern, then we can apply the antiderivative without doing that substitution. So as I'm looking at this again, I was looking for something that was on the inside to represent my inside function of g of x. And I've got 5x plus 1 representing that inside function. Now, I would need the derivative of that. I would need the derivative of that inside function in order to proceed with the pattern. The derivative of 5x plus 1 would be 5, and I don't have that right now, but I can multiply by 5 over 5 to create that 5 that I need. So that would give 1/5 the integral of 5 over 5x plus 1 to the 6 dx. Now another thing that's sort of throwing me off from this pattern is that the outside part, so the outside part would be the 6th power, is in the denominator, which is a little confusing. So I'm going to bring that into the numerator and write this as 1/5 the integral of 5x plus 1 to the negative 6th power times 5 dx. So now when I look at this, I see the exact pattern that we were talking about up here. We have an inside function, which is our g. We have the derivative of that inside function, and then we have our outside function, and our outside function is a power. And so this f and the antiderivative of f will be following the power rule because f is a power. So that tells me that outside function tells me the antiderivative rule to follow. So I'm going to carry down that 1/5. I'm going to calculate the antiderivative using this outside function. So I'm going to add 1 to the power and divide by the power, leaving the inside alone. And then I need my plus c. So that gives me negative 1/25 times 5x plus 1 to the negative 5th plus c. And I can move that factor down into the denominator using my exponent rule. So that's negative 1 over 25. And negative 1 over 25 times 5x plus 1 to the 5th power plus c. On this question, we want to evaluate the integral. We've got the integral of square root x minus 2 over x squared dx. So in this example, we notice that we have a fraction and some individual terms in the numerator. So what we're going to do is use a little bit of algebra to break this up into individual terms. So we're going to write this as square root of x is the x to the 1/2 power. And we're going to divide that by 2 and then break up this fraction so that we have 2 over x squared. And we can use a little bit more algebra. This is x to the 1/2 over x squared. They have the same base, so we can apply the quotient rule for exponents and subtract those exponents. So that would be 1/2 minus 2 And on the other term, I would write that using a property of exponents to make that x to the negative 2. So this is the integral of x, and 1/2 minus 2, that's 1/2 minus 4 over 2. And that is the integral of x to the negative 3/2 minus 2x to the negative 2 dx. So we've done a bunch of algebra to clean this up so that we can apply our power rule. Our power rule for integration is that we're going to add 1 to the power and divide by that power. So we're going to do x to the negative 3 over 2 plus 1 over negative 3 over 2 plus 1 minus 2x to the negative 2 plus 1 over negative 2 plus 1 plus c. Negative 3 over 2 plus 1 is negative 1/2. And we've got negative 2x to the negative 1. Negative 2 plus 1 is negative 1. And I'm going to multiply by the reciprocal for this part, so this becomes negative 2. And I'm also going to move this factor down to the denominator because of that negative x in the exponent. So that becomes x to the 1/2. X to the 1/2 power minus, that'll become a plus, negative 2 and negative 1 make a plus. And I can move that factor down to the denominator. And finally, I can change that x to the 1/2 power back to a radical. So you've got negative 2 over square root x plus 2 over x plus c. On this question, we want to use logarithmic differentiation to differentiate the function with respect to x. So we have the equation y equals 2x to the 2x. And to use logarithmic differentiation, we're going to take the log of both sides. We're going to do natural log because natural log has the easiest derivative rule. So we're going to do natural log on the left and natural log on the right. Now, one of the reasons why we introduce the logs is because the log has all of these expanding properties. We have the product rule, the quotient rule, and the power rule, which allows us to expand and condense these logarithms. So it's very flexible when we have logs within our expressions. So when I'm looking inside this log on the left-hand side, the first thing I notice is that I have a product. So I'm going to use the product rule for logarithms. And as I do this product rule, I just want to remind you that this is an algebra property I'm using and not a calculus property at the moment. So far I've used a log property to take the log of both sides, which is an algebra property. And I'm going to use the product rule for logs, which is an algebra property. So that gives natural log y equals natural log 2 plus natural log of x to the 2x. And then I'm going to use another algebra property called the power rule, and it's going to allow me to take this power and move it into the coefficient on the log. So this is natural log of y equals natural log of 2 plus 2x natural log x. And now that I've expanded this, I'm ready to do some calculus. So what I'm going to do is calculate the derivative on both sides of this equation. And I'm going to calculate the derivative with respect to x on the left and the derivative with respect to x on the right. We're balancing doing the same thing on both sides of the equation. And on the left-hand side, we notice that our variables do not match each other. And so when the variables don't match, you have to use implicit differentiation. And that's going to give me a derivative of y prime over y. On the right-hand side, the variables do match. And so I'm going to calculate the derivative, and that is derivative of natural log 2 is 0, because it's a constant, and the derivative of 2x natural log x, I need to use the product rule since we have a variable in the factor of 2x and a variable in the factor of natural log. So that's the first times the derivative of the second plus the second times the derivative of the first. And that gives y prime over y equals 2x. The derivative of natural log x is 1 over x. And natural log x, the derivative of 2x is 2. So these x's cancel each other out. And I'm left with y prime over y equals 2 plus 2 natural log x. And I'm going to multiply both sides by y so that I can solve for y prime. So I'll multiply by y on the left and multiply by y on the right. That gives y prime equals y times 2 plus 2 natural log x. And I'm going to zoom out here so we can see the original problem. In the original problem, we were given that y is equal to 2x to the 2x. So this is 2x to the 2x times 2 plus 2 natural log x. And this is correct, but these are both 2, so they have a common factor of 2. So I could factor that common factor out. If I factor that common factor out, we would have a 4 here. And then we would have 1 plus natural log x. So that is a completely factored version of that expression. So on this function on this example, we're given the function f of x equals 2x plus 5, and we want to approximate the area under the curve on the interval from 0 to 2 using 4 rectangles. So first I want to draw a picture of what's being asked of us. Let's draw the function f of x equals 2x plus 5. So let me draw it a little bit off center since we're only looking at 0 to 2. And we have a y-intercept of 5 and a slope of 2. So we're looking at the curve, or the straight line, 2x plus 5, on the interval from 0 to 2. So I'm going to draw a vertical line at 2. And this is the area that we would like to approximate. So the area under this curve in between 0 and 2 and the x-axis. And we want to use 4 rectangles. So if I zoom in on this a little bit better, you zoom in on this picture here, I'm going to have my rectangles occurring at a half, 1, 1.5, and 2, and those are going to be my different rectangles. From there, I can draw up to the curve And it says that I should use right endpoints and left endpoints to approximate. So we're going to have an approximation using the right endpoints and the left endpoints. I was specifically asked to do the left endpoints. So if I use the left endpoints, I'll be finding an area that is a little bit smaller than the actual area. So when we say we're going to use left endpoints, what that means is that you use the left endpoint to find the height of that rectangle. So if I use the left endpoint here, I have a height that's a little bit less than the actual curve, and the left endpoint here, the left endpoint here. Now we can get the sequence of those left endpoints with some formulas that I have over here on the side. So in this example, we need to identify what the width of each rectangle is. We call that delta x. And so that's going to be b minus a over n. A and b are our interval. So we have 2 minus 0 over n, which is the number of rectangles. And that works out to be 2 over 4, which is 1/2. And that's why I drew each of these rectangles to have a width of 1/2. And we're going to focus on the left endpoints. We have a formula for the sequence of left endpoints, and that is a plus delta x times I minus 1. So a was 0. Delta x is 1/2. And then we have our sequence generator, I minus 1. So 1/2 times I minus 1 will give us all of the left endpoints. And we can check that visually with our graph here. So let's let I equal 1. If I equals 1, then the sequence is 1/2 times 1 minus 1, which is 1/2 times 0, and that's 0. And the first left endpoint that we have, let's see if I can mark that in a different color so you can see where I'm marking it. That first left endpoint is at 0. If I is equal to 2, then 1/2 times 2 minus 1 is 1/2 times 1, and that's 1/2. And that second left endpoint is at 1/2. If I is 3, I have 1/2 times 3 minus 1, 1/2 times 2, and that's 1. My third left endpoint. And then we have one more, I equals 4. That's 1/2 times 4 minus 1, 1/2 times 3. That's 3/2 or 1.5, and that gives me my third left endpoint. So that is the formula that gives me the sequence of left endpoints, as long as we're doing equal width intervals. So then we want to find the area. So we have this formula for finding the area, the approximate area. And we're going to use the left endpoints. We have the sum of I equals 1 to n. N, remember, is the number of rectangles. We have 4 rectangles. And that's going to be delta x. That's 1/2. That's the width of each of our rectangles, times f. At our endpoints, we're using the left endpoints, and I'm going to use the sequence 1/2 times I minus 1. Now we're doing f of that. That's the y value. So I need to use our function that we've established. That's going to give me the height of my rectangles. So I'm going to substitute that 1/2 I minus 1 into the function f of x equals 2x plus 5. So I have the sum of I equals 1 to 4 of 1/2 times 2. That's 2 times 1/2 I minus 1 plus 5. That 1/2 is times all of that. And I'll do a little bit of cleanup here. I'll distribute this 1/2 to both of these terms. That's the sum of I equals 1 to 4. The 1/2 times 2 cancel each other out. And I'm left with 1/2 I minus 1. And then 1/2 times 5 is 5 over 2. And let's clean up a little bit more. I'll distribute that 1/2. And that gives me 1/2 I minus 1/2 plus 5/2. Sum I equals 1 to 4. 1/2 I minus 1/2 plus 5/2. I can combine the minus 1/2 and plus 5/2 together. That's the sum of I equals 1 to 4 of 1/2 I minus 4 over 2. Sorry, that's plus 4 over 2. And that's the sum of I equals 1 to 4 of 1/2 I plus 2. One of the properties of the summation notation is that you can apply the sum to individual terms. So I can do 1/2 sum I equals 1 to 4 of I plus sum I equals 1 to 4 of 2. And these sums are easy to work out by hand, but we also have formulas that we can use to work them out. The sum of I equals 1 to n of I is n times n plus 1 over 2. And the sum of I equals 1 to n of a constant is that constant times n. And remember, our value of n is 4, so that's what we're going to use in the formula. So we can do 1/2 times 4 times 5 over 2 plus 4 times 2 times 4. And so this becomes 5 plus 8, which is 13. So the approximate area using the left endpoint is 13. Yeah, on this question, we want to evaluate the indefinite integral of 2x over x squared minus 9 to the third power dx. And when I initially glance at this, what I'm looking for is something that I can use substitution on. And when I use substitution, I'm looking for a portion that I can let be u, and then I also want to have the derivative of that u within my expression. So let me write out what pattern I'm actually trying to follow here. And what I'm looking for is to have a function on the outside and a function on the inside. This is a composition of two functions. And I need to have the derivative of the inside function in my expression, multiplied onto my expression. And if I have something that fits this pattern, I'm going to follow this integration rule where we use the outside function to find the antiderivative. So I'm going to use a capital F to represent the antiderivative of lowercase f. And we would leave the inside alone and then add our constant c for the family of antiderivatives. So as long as I have this pattern inside the integral, I'm going to be able to apply this pattern of calculating the antiderivative on the outside part. So once again, let me just sort of repeat what I said at the start. So if I'm going to use this substitution rule, I'm looking for something that I could let be my u, and that's the inside part here. And then I need to also have the derivative of u within my integral and multiplied onto my expression. So when I'm looking at this integral, I'm noticing that inside the parentheses I have x squared minus 9. The derivative of x squared minus 9 is 2x. And so I can see that pattern within what I have here. So let's rewrite our problem, and I'll show you how to do this with substitution, and I'll show you how to do it with pattern recognition. So I've got the integral of 2x over x squared minus 9 cubed dx. I'm going to let u be that expression inside my parentheses, that's x squared minus 9. And I'm going to calculate the derivative of u with respect to x, and that's 2x. I'm going to make this substitution. I'm going to change the x's to u's, and I also need to change the dx to du. So I'm going to rearrange this, multiplying by dx on both sides, that's 2x dx, and dividing by 2x on both sides gives me dx equals du over 2x. So now I'm going to do the substitution, and I'm going to substitute in for the x squared minus 9, I'll put u, and in place of the dx, I'll put du over 2x. And that's going to give the integral of 2x over u cubed times du over 2x. If I do a little simplifying here, the 2x's cancel, and I'm going to use my properties of exponents to bring that u cubed up to the numerator. So it will be the integral of u to the negative 3 du. So then I'm going to apply the power rule, antiderivative, and the power rule, I add 1 to the power and divide by that power. So this is u to the negative 3 plus 1 over negative 3 plus 1 plus c. And then I have u to the negative 2 over negative 2. Left off my plus c there. And if I rewrite this, I would have negative 1/2 u squared plus c. And the final thing I want to do is bring back that original variable. We want to have x's instead of u's. So this is negative 1 over 2 times x squared minus 9 squared plus c. And so we calculated that integral with substitution. So I'm going to try this again, but with pattern recognition. So I am going to start off with the original problem, and I have 2x over x squared minus 9 cubed dx. And the same thought process that we were talking about earlier with substitution is there. You're still looking for something to be u and needing the derivative of that within your expression. But then I'm going to rewrite this using my exponent properties. I'm going to be able to bring this factor to the numerator. So that's x squared minus 9 to the negative 3. Times 2x dx. And as I look at this, I am noticing I've got my inside, which is g, then I've got g prime here, and my outside function is this power. And I have matched this to the pattern that we were looking at earlier. The pattern we were looking at earlier has an outside function, an inside function, and the derivative of the inside function. We have the outside function the inside function and the derivative of the inside function. So that means I can follow this rule in which I need to calculate the antiderivative on the outside function. My outside function is a power, so I'm going to use the power rule. So I add 1 to the power and divide by that power and do the plus c. And we can simplify that to be x squared minus 9 to the negative 2 over negative 2 plus c. And we can simplify that again using our properties of exponents to make this negative 1 over 2 times x squared minus 9 squared plus c. So you can see we get the same answer whether we're using the substitution method or the pattern recognition for the composition of functions. In this question, we want to solve the problem using calculus techniques. Show your work on scratch paper for full credit. We want to find two numbers whose difference is 100 and whose product is minimum. So we want to find the product, which is minimum, and this is the function that we want to build to do the calculus on. So we know that we have two numbers. I'm going to give variables for the two numbers. So let's say the first number is x and the second number is y. We can say that the product of those numbers is xy. I'm going to simplify that and say p is xy. Now, right now, because we have two variables in our equation, x and y, we can't use the calculus techniques. We're doing one variable calculus. So we're going to use some of the other information in the problem to try to reduce the number of variables that are in the equation. So we're going to use this information to find a secondary equation. So we know that these two numbers have a difference of 100. So we know that x minus y is equal to 100. You could have also done y minus x because it doesn't specify. So we have x minus y equals 100. We can now solve for x by adding y to both sides, and that gives x equals y plus 100. We're going to take that information and substitute it into our primary equation, the equation that we want to do the calculus on. I know that this is the equation I want to do the calculus on because it says we want to find the minimum value. It could also be the maximum, largest, smallest. So once we make that substitution, we're going to have y plus 100 times y, and we can simplify that becomes y squared plus 100y. So now we have an equation with only one variable, p equals y squared plus 100y, and we're going to do our calculus techniques on this. So we first want to find our critical numbers. So we're going to calculate the derivative. That's 2y plus 100. We'll set that equal to 0 to find our critical numbers. Critical numbers are where the derivative is 0 or undefined. So let's subtract 100. We get 2y equals negative 100. Divide by 2, and y equals negative 50. So that's our critical number. And then we're going to use the second derivative to test and see if this critical number is a minimum or a maximum. So let's calculate the second derivative. So I'm using the first derivative to calculate the second derivative. And the second derivative would be just 2. We've got the second derivative being positive. And when the second derivative is positive, that means concave up. And concave up means that we have a minimum at our critical number. So it's combined concave up at a critical number. Critical number means we have a horizontal tangent line. Concave up is that up facing, and so that creates a minimum at the critical number. And so we know that we have a minimum when y is equal to -50. And our directions up here say to find the two numbers. So I've already found y, and I can find x using this equation right here. X equals y plus 100. That's -50 plus 100. And that is 50. So the two numbers that will produce a minimum product are 50 and -50. On this question, we want to discuss the continuity of the function, state the interval where the function is continuous, and whether the discontinuities are removable or non-removable. So what we're given is a piecewise defined function. That's f of x equals x squared minus 1 whenever x is less than or equal to 2, and -2x plus 7 when x is greater than 2. When we look at these two equations individually, these are the equations y equals x squared minus 1 and y equals -2x plus 7. Y equals x squared minus 1 is a quadratic, which is a type of polynomial, and quadratics and polynomials are defined and continuous over all real numbers. So certainly it will be defined and continuous on this interval where x is less than or equal to 2. The equation y equals -2x plus 7 is a linear equation, which is a type of polynomial, and it is also defined and continuous over all real numbers and will be defined and continuous on the interval from where x is greater than 2. So our only concern with this piecewise defined function is where we join them together. And we are going to join these equations together at x equals 2. So we really want to test the continuity at that particular spot. So we have three criteria for a function to be continuous at a point. First, you need f of that value to be defined. So I'm going to erase my circles here so we can see this first equation is the one we're going to use to define f at 2 because it has the equal to. So we have f of 2 being 2 squared minus 1. 2 squared minus 1 would be 4 minus 1, and that's 3. So the function is defined at x equals 2. Now the second criteria for continuity is that the limit needs to exist. The limit as x approaches 2 of f of x needs to exist. Now because this is a piecewise defined function, we're going to look at the one-sided limits. So we're going to look at the limit from below as x approaches 2 from below. And we're also going to look at the limit from above, the limit as x approaches 2 from above. Now when we have x's that are below 2, we're going to use that first equation. That first equation says that x is less than 2. So when we're below 2, we need to use that equation to find this limit. So that's going to be 2 squared minus 1. 4 minus 1, which is 3. And then when we find the limit from above, 2 plus, we need to use the second equation because we use that second equation when x is greater than 2. So we have negative 2 times 2 plus 7. That is negative 4 plus 7, which is 3. So that limit does exist because these one-sided limits are matching each other. So the limit as x approaches 2 of f of x is 3. And the third criteria for continuity is that this function value and the limit agree with each other. So the limit as x approaches 2 of f of x equals 3, and the function value f at 2 equals 3. So they agree with each other. The continuity criteria has been met, and so we know that this function is continuous at x equals 2. And that was our only concern, and we've already stated that it's going to be continuous for less than 2, continuous for greater than 2, so this function is continuous from negative infinity to infinity. There will be no discontinuities. And since there are no discontinuities, we don't have a type for that discontinuity. So the interval where this function is continuous is negative infinity to infinity, and there are no discontinuities. Thank you for checking out my videos. Have a great day.